Hi, in this video, we're going to go over the solutions to Worksheet 7.5. So we got ourselves a 200 kilogram box, which is a pretty heavy box, and it's being pulled by this little motor here. The box moves a distance of 2.5 meters across the horizontal surface. The force of friction on the box, um, right, is 392 newtons. So, says first draw a force diagram. Okay, it's been a little while since we've done that. So we have the force of gravity, normal force, force of friction, and the tension force would be the same. Let's see here. All right, those two have to be the same force because let's remember that it's being pulled at a constant speed. So constant speed means the force to the right would have to equal the force to the left. So construct a qualitative energy bar diagram for this situation. Be sure to specify your system. So in this case, we would put just the block in the system. We would not put the engine in the system, the little motor, because otherwise we'd have to tell it, say what kind of, is it electrical motor? Is it a gas motor? Like what kind of a motor is it? So now we could put kinetic energy in the system. However, since the kinetic energy is not increasing or decreasing, that's because it's moving at a constant speed. I'm just going to leave that off. And that's just because it doesn't, when I go to write my equation, it's just going to kind of mess things up a bit. So we know that we are adding energy here. This would be from the motor. And we also know we're losing energy. That didn't turn nice. To friction. So you can put kinetic energy, like you could put one bar here, one bar there, that would be fine. So I'm not going to. So, or I mean, okay, we can put them in there. Um, it doesn't really matter. When I go to solve my energy equation, I'm just going to end up canceling those out because they're the same amount. How much energy was transferred by the engine? So we call that work. Work is equal to force times by distance. And so the force is 392, right? Wasn't that what it is? 392? Yep, 392. Times by the distance, we pull it 2.5 meters. And so that would be 980 newtons. Okay, how far could the box be pulled at a constant velocity with the expenditure of 8,000 joules of energy? So now we know, right back to our work is equal to force times by distance equation, we know that the little engine has put in 8,000 joules worth of energy. Oh, I wrote newtons up here, sorry. That should be joules. We know that we put in 8,000 joules worth of energy. The force is the same, still 392, because we're still moving at a constant speed. So, right, so that means it's pulling with the same amount of force. And then I just want to know how far am I going to pull it, which is x. So 8,000 divided by 392 gives us 20.4 meters. All right. Lastly, what will happen to the speed of the engine if the or speed of the block if the engine pulls with 5 newtons? Modify your force diagram. Apply Newton's second law to help you answer this question. Then draw a new energy bar graph. So, um, the speed of the block will now increase because there is now a net force to the right. If we take a look at draw the force diagram for that, gravity will be the same. Normal force will be the same. Force friction will be the same, right? But now we have T equals 500 newtons over here. So, right, we see that we have a bigger force to the right that's going to cause this block to accelerate to the right. So, let's see here. Again, we're just going to put the block in the system. So now we're going to put, if we compare it to the one that we just made, right, up here, I had 4 bars of energy going in, so I need to have more than that. I should have maybe planned ahead, not put quite as many bars in. So I guess 1, 2, 3, 4, 5. Seems like almost should be 6 in there. Let's do that. So we still lose the same amount to friction. And we had 1 in plus 6. So that gives you 7 minus 4 gives you 3. So there you go. Right, so just kind of noting, I have more energy going in because now the tension is greater, so the engine is going to put more energy in, so hence I have 6 bars of energy going in. Last time when I look up here, I put 4 bars of energy going out, so that would remain the same. I still need to have 4. Just counting them up, I have 1 bar of kinetic energy plus 6 bars of energy in, so that's going to give me a total of 7. Then I lose these 4, so that leaves me with 3 left that are going to become kinetic energy. So there you go. There's the first one done. Number 2. So you push a 45-kilogram wood crate 10.5 meters up a hill ramp that makes a angle 22 degrees, so horizontal at a constant speed. The force of friction is 157. Draw a picture. So there we go. Here's degrees. Here's our crate. There you are trying to push it. So, and it is 10.5 meters up the ramp. So, it says draw an LOL graph of this situation. So, looks like we have the crate in the system. And that's the only thing I'm going to put in there. You don't want to put U in the system because you're putting the energy in. I'm going to say it does move at a constant speed, but I'm going to go ahead and leave off the kinetic energy. In this case, even though I put it in there last time, because I am actually writing the equation, it's going to mess it up. I guess here, put one in. So because I'm moving at a constant speed, and I'm going to end up crossing that out later. So but then we have the person who's putting some energy in. So I'll put 4 bars of energy in, and then some of that energy is going to go out to friction. Doesn't really matter how much you have going outwards. I'm just going to have 1 bar, and then that's going to leave me with 3 bars of gravitational energy. So, so use the LOL to graph to write an energy equation. You don't have to solve it yet. So let's see here. We would have kinetic energy plus work in, that's from me, minus the work from friction equals kinetic energy plus gravitational energy. Real quick, I'm going to go ahead and cancel these kinetic energies because they are the same. So okay, so there we go. Next, it says use trigonometry to find the height in the crate. What is the increase in gravitational potential energy? So let's see here. We basically have this, the height or a length of 10.5, and the angle is 22 degrees, and I would like h. That means I have the hypotenuse of the triangle, and I'm looking um, for the opposite, and so that's going to be sine 22 degrees is equal to h divided by the 10.5. So then multiply both sides by 10.5. So 10.5 sine 22 is equal to h. H is equal to 3.93, let's just call it 3.9 meters. So then what is the increase in gravitational energy? It's just mgh. So let's see here, m, pretty sure we're given that up above, 45 kilograms. So 45 kilograms times by 9.8 times by the height, 3.9. That means that the gravitational energy has increased 1,720 joules, depending on how you round. But so those are the two things that we were asked to find in that equation or in that question. Okay, so now solve the energy equation to find the amount of work you did to get the crate up the slope. Okay, so let's look what we have left after we crossed out the kinetic energies. We had work in, which is what we're being asked to solve for because that's the amount of work we did pushing it up there, minus the work due to friction is equal to the work or is equal to the amount of gravitational energy. Okay, so again, this is what we're solving for. So work in, we'll leave that there, minus the force or the work due to friction. That is going to be the force of friction times by the distance we pushed it uh, is equal to the gravitational energy, which we know, right? So and minus force of friction was given up at the very top, 157. So we'll put that in there, 157 times by the distance we push it, which is 10.5 meters, right? That's the length of the ramp, is equal to the amount of gravitational energy. That's 1,720, which, right, so it's the amount of energy I put in minus, right, I lose a little bit to friction is equal to basically how much energy how, gravitational energy I've given. So let's see here, that's going to be 157 times by 10.5, 16. Okay, by a little bit, I mean most of it we lost. Oh no, like half of it, right? Add the 1647 to the other side, so you're going to get, we put in about 3,368.5 joules of energy. So, right, about half of it was lost to friction, the other half became gravitational energy. All right, so that's number 2 done. On to number 3. So the tricky part about number 3 is that we're pulling it at an angle. So the first thing is to draw a force diagram. So there we go. We got force of friction. We're pulling it at an angle. Make sure the normal force is smaller than the force of gravity because you're lifting up and pulling to the left there. So next up, how much force acts in the direction of motion? So what that means is how much of the force that you pull with acts in the direction of motion. So to do that, we're going to have to break this up into pieces like we used to. So that's going to be 100 cosine of 30 degrees. We're not probably going to need this, but we'll do that too. 100 sine 30 degrees. Okay. So, how much of the force acts in the direction of motion? So to answer that question, the force that acts in the direction of motion is the 100. So we can go ahead and 100 times by the cosine of 30 degrees. It's going to give us 86.6 newtons. So that's the first thing it asked us. How much energy is transferred to the box via working by the person who pulls the box at 10 meters? Okay, to answer that question, work is equal to force times by delta x. Remember that force is only the direction, or the force that is parallel to the direction of motion. So we've already found that, that's the 86. So work is equal to 86.6 times by 10 meters. It's 866 joules of energy. All right, so that means we have put in 866 joules worth of energy. Next, it says sum the horizontal forces on your object and find the acceleration to find out if the box is moving at a constant speed. What does this tell you about the system? Okay, sum the forces in the x direction, set it equal to ma because the thing is accelerating. Forces to the left, we have our 100 cosine 30 minus the forces in the other direction, which would be that 66. So let's see here. The mass of the object is 50 kilograms. So 50 kilograms times by A, because that's what we're solving for. That's going to be the 86 minus 66. So 50A is equal to 86.6 minus 66, which gives you 20.6. Divide by 50, and you get your acceleration 0.4. We'll just go with that, we'll round it. Units on acceleration, remember, are meters per second squared. So this tells us the, what is it, block, crate, what is it, box. Box is speeding up, which means amount of kinetic energy is increasing. So draw an energy bar graph. Let's assume this thing starts at rest. So we'll start out with no kinetic energy. We'll put the box in the person or in the system. We have some energy coming in from the person there. From person, we're losing some energy to friction. I'll put 2 because I feel like it could be 1. So there we go. Some in the kinetic energy, right? So we're seeing our kinetic energy increase. How fast is the box going after being pulled for 10 meters? Again, on that, we'll assume that it starts from rest. So we have the work in minus, and you could do this using kinematics as well, but the idea, the point is to practice our writing our equation. But if you did kinematics, it's not a problem using meaning Paul-John Ringo equation equals kinetic energy. So that would be the amount of work in. Let's see here. We calculate that. We know we put in 866 minus the amount of energy we lose to friction, which would be 66 times by 10 is equal to 1/2 mv squared. So 866 minus 660 to 1/2. Again, I believe it's a 50 kilogram block. V squared. So 866 minus 660, 206 joules to 25 squared divided by 25. It's going to give you 8.24 equals v squared. Square root both sides equal to 2.87 meters per second. So there we go. All right. Well, I hope this helps. As always, if you end up with any questions, feel free to ask me. But thank you for watching.